Hello and welcome back to Probability Theory, the video series where we talk about stochastical processes and statistics. And indeed, in today's part 36, we continue our discussion about statistical models and point estimators. I will show you an explicit example of such a point estimator, and we will also define the term consistency. However, before we do that, as always, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And as you might already know, you can use the link in the description to download additional material for all the videos. And then without further ado, let's immediately recall what a statistical model is. There we just have a subset Xn in Rn, the Borel sigma algebra on it, and a whole collection of probability measures. In fact, p theta here is a probability measure on R, but because we have Rn, we take the n-fold product measure. And now one of the simplest statistical models is when we choose our parameter space capital theta as an interval in R. Hence, any point theta in the interval gives us a well-defined probability measure p theta. So you could say for a fixed theta here, we have a nice ordinary probability space. And with the product measure, it's defined on our statistical sample space, which we call Xn. And there, please don't forget, a point in the sample space consists of n coordinates. So alternatively, you can just say that we have n values in R given as our sample. And this is really important because the only information we have in statistics is such a sample. And we usually write such a sample with lowercase x1, x2, and so on. So there we have n independent measurements, which means we could also say they come from n independent random variables. So clearly what we have here are IID random variables, so independent random variables, which are also identically distributed. And these ones we would denote by capital X1 to Xn. So they are essentially the same, but we don't know them, and that is the reason we need statistics. So more precisely, what we want to find here is the distribution, so for example px1, which in our model just means which is the correct theta, such that p theta is given by px1. So this is what we want to do in statistics. We want to find the correct theta here, but we don't have enough information for that. Therefore, we have to estimate it, and one possibility is a so-called point estimator. And this one we usually denote by Tn. And here you see, it gets a sample as an input, and the output is a suitable theta in the parameter space. So different samples can definitely give us different thetas, but they should be close to the underlying correct one. And since we simply don't know the correct theta, the art of statistics is that the estimator works with its definition no matter what the correct theta is. And now I think the best way to understand all of that is to look at a very concrete example. And this is a quite standard one because we assume that we just have a machine that generates random numbers. So let's say you push a button and then a real number comes out. So not so complicated, we can have integers but also decimal numbers. And moreover, negative numbers are also allowed. And now the first step in statistics is to choose a suitable statistical model. And here it would make sense that the random numbers come from a fixed interval and are uniformly distributed. So the assumption is that we have uniform distributions and an interval from minus theta to plus theta. But we don't know the bounds of the interval, so our theta is unknown. So here we can say we don't know the explicit interval the machine is set to, but we want to extract this information by looking at samples. And in order to do that, we write down our statistical model and choose a suitable point estimator for it. So first, the sample space we have to choose here should be Rn, because any real number can come out of the machine. And then as the sigma algebra, we just have our Borel sigma algebra on Rn. And then most importantly, the collection of probability measures is given by uniform distributions. So in short, we have the uniform distribution on the interval from minus theta to plus theta, and then we form the product measure. And in order to keep it short, I just put an n here and say this is the n-fold product measure. So this should not be the problem, because now we want to talk about something more important, namely the parameter space. Namely, our theta here could be any non-negative real number. So the parameter space we have is given by 0 to infinity. This is quite important because we don't know anything about a limitation of this interval here. Okay, so this is our statistical model, but now actually the only information we have is a given sample. So a collection of n values, which we call x. So we have n random numbers and they don't have to be ordered, but let's say I've ordered them here. Then we definitely already know that our theta cannot be less than 6 or even less than 7. Otherwise, the -7 here could not have been produced. And this already leads us to a first idea of a point estimator. So if we have a sample x given, then we can choose Tn of x as the maximal amplitude, meaning that we take the maximum of the absolute value of the coordinates. So quite a simple formula, we just have max of the absolute value of xj. So in our example here, this would give us Tn of x as equal to 7. So our point estimator says, seeing the sample, most likely theta is given by 7. Indeed, we have a reason to believe that, but we already know that this point estimator is biased. This is quite clear because we already know that it is really unlikely that we actually would pick the boundary point as a random number here. However, on the other hand, it's quite likely that we pick points close to the boundary. So in other words, this point estimator here will underestimate the value of theta. And in order to show that, let's calculate the bias as we have defined it in the last video. There, essentially, we just have to calculate the expectation of the point estimator. And please don't forget, this expectation here is just with respect to the product measure p theta n. So if you prefer it, you can always write it as an abstract integral. So in general, we just would integrate about the sample space xn, and then we have the point estimator inside. And then everything with respect to p theta n. So in order to calculate the bias, we just have to solve this abstract integral, and that would be really helpful to have the probability density function of this random variable Tn. And in order to get that here, it's actually easier to calculate the CDF first. So there, please recall, the cumulative distribution function just calculates a probability of an interval. So more precisely, we have p theta n of Tn less or equal than a given constant c. Which means here that the maximum in the absolute value has to be less or equal than c. So we just have the set of all samples that satisfy this. Hence, every input of the sample has to be less or equal in the absolute value than c. Which means we can write down the set with n conditions. But this also implies that we can write this whole set as an intersection of n sets. The first set has the first condition, the second set the second condition, and so on. And there you might already know, we want to write it like that because we want to use the independence. Indeed, by assumption we know that the random numbers are picked independently, so these events here are definitely also independent. Which immediately implies that we can write it as a product with n factors. And this is quite helpful because now we just have to calculate the probability of this event. And this is not a problem at all because we just have the uniform distribution there. And here we just have a condition for the first component. All the other components can go from minus theta to plus theta. However, x1 here can only go from minus c to plus c, so we have 2c as the length of the interval. And by the uniform distribution, we just have to divide this by the whole interval, which is from minus theta to plus theta. So the length is 2 theta. And clearly we can do the same calculation for all the other factors in the product as well, because they just consider different components. And clearly that does not change anything for the calculation, we still get out c divided by theta. And indeed, this is the nice general result we get for our CDF here. So we have c divided by theta in the product n times. However, clearly this whole calculation only makes sense if c is between 0 and theta. In fact, in the case that c is greater than theta anyway, then we don't have any restriction here and we just get out the probability as equal to 1. And moreover, if c is less than 0, so a negative number, the probability has to be 0. And with that we have covered all the cases and we have the whole CDF for our point estimator Tn. And now, as you might remember, we actually want to calculate an integral with Tn, so the PDF would be helpful. And this probability density function is connected to the CDF, as you might know from our earlier videos about probability theory. In fact, integrating the probability density function from -infinity to c should give us the CDF. So going backwards from the CDF to the PDF means that we have more or less a derivative. This means f of s definitely has to be 0 on the outer intervals here and there. And the most important information we find again in the interval from 0 to theta. So first we have the constant theta to the power minus n times s to the power n minus 1. Very well, now we can check. Integrating that definitely gives us the CDF back, so we can use this PDF for our expectation. As already mentioned, this expectation is an abstract integral where we can use the change of variables formula. So if you want, you can say we have a substitution where Tn of x is equal to s. And then this simply leads to an integral over r. And the probability measure in the integral is just our distribution of Tn. However, now we already know that the distribution of Tn can be expressed with the PDF. So you see, this is just the continuous case for this calculation. The expectation is the integral over r of s times f of s. So not so surprising, but now you see again where it comes from. So in the end here, we just have to solve a one-dimensional integral. And actually it just goes from 0 to theta. And then we have s times the PDF, so we have s to the power n here. So it's just a polynomial, so not a complicated integral at all. So the result is 1 over n plus 1 times s to the power n plus 1. And then we simply put in 0 and theta. And then we can cancel everything, and what remains is n over n plus 1 times our constant theta. And that's it. This is the result of the expectation. And as you can see, we don't get out exactly theta as we would get for an unbiased point estimator. Indeed, this is what we have already expected, that we have a slight bias to underestimate theta. So systematically, we will always be a little bit smaller than the correct value theta. But you can also notice that this does not matter so much if n is really large. Nevertheless, we should correct our point estimator here to get a real unbiased one. This is quite simple now, because we have already done the whole calculation to see what an unbiased point estimator is. Let's call this one Tn tilde, and let's use almost the same definition as for Tn. The only difference is now that we scale it with the correct factor. And this one will be n plus 1 divided by n. So by making this estimate a little bit bigger, we get an unbiased point estimator. So this completely removes our bias, which means that our expectation is now nice enough. However, now we can imagine if the variance of this point estimator is really large, then it's also not a good point estimator. If we deviate a lot, we don't get much certainty for our correct value theta. This is what we usually put into a box labeled efficiency, and definitely something we will discuss in future. But first I want to define the term consistency, which cares about what happens when we increase our sample size n. So a bigger sample size definitely means that we have more information to deal with. So in some sense we could assume that our point estimator Tn is also stronger. So we can just look how likely it is that we deviate from the real value theta by epsilon. So the epsilon here is fixed, so we get out a probability, but then we want to increase the sample size n. And the point estimator is called consistent if a bigger sample size really helps us here. So in the limit of infinite information for us, the point estimator is completely correct in probability. And as before, this should work no matter what the correct value of theta actually is. And please note, the error epsilon here is completely fixed in the limit process. And then as already mentioned, if we have this nice property, then the whole sequence of point estimators is called consistent. Indeed, you are allowed to say that the point estimators converge in probability. And moreover, here I can already tell you, because we have Chebyshev's inequality, this property here is related to knowing what the variance does for n to infinity. So in summary here you can see that we have to put in requirements for a point estimator such that it can be used in statistics. So we definitely need to know how good the thing works in theory before we can apply it to the real world. And moreover, there we definitely also want to quantify how likely our estimate actually is. And because of that, we will also often work with interval estimator, which give a whole interval back. However, this is definitely something for the next videos, so I really hope I meet you there again, and have a nice day. Bye bye.